Oh, well, welcome for those of you who are here on time. Uh, First, I wanted to start out with having you work on this problem. I have two problems to work on, so if you're here already, you might as well get started. The two main things that you should learn in this section are how to get critical defects and how to do life analysis. So I'll put these up for a little while. Here's critical defects, and this is life. We'll hit the life after the critical defect. Critical defect shouldn't take too long, but has a little bit not quite tricky. You want to have an edge-loaded crack and loaded in tension to 250 kips, and the plate is 5 inches wide and 1 inch thick. Use K1C that we got before is 81. If you've forgotten that, it's 81, and yield strength is 100. And then what happens if you double K1C but half the yield strength? You might, well, you need your handout, and let me show you what you should have. You probably need to use this one, single edge crack. That's the geometry that I wanted you to use. So you could use that one, and you should have that on the handout. So I'll put back up the main thing here, which is this, and give you some minutes to work on that. Did anybody get to upload lectures yet? Didn't come yet? Or they did?
Sir, only 2 days lectures are available.
2 days?
2 days, starting 2 days.
Not yesterday. Not. You should get all first week. Would be a good thing. The critical page you need is toward the back of that. It's the second, not the back side, but the one of the last pages. Should be one that says, oh, it's double-sided?
Yeah, double-sided.
Okay, save paper. In my solution, so try to fix that. I think it's okay. Go back to the details here. Critical defect size for load of 250 and 5-inch by 1-inch plate with an edge crack. And you should use the single edge crack solution or table to get the capital F. So in this case, I wanted to use the capital F form and find the stress being 50, 250 divided by 1 by 5. Want to point out again, when you calculate stresses, you never put the defect in. The defect comes at 2 places. You don't need it at a 3rd place. So that's the way all the case solutions are set up, that the stress is calculated without the defect. So first of all, you assume the whole plate, 250 divided by 1 by 5 is 50, and then use this K form. Now, crack length is under the radical. Crack length is part of the F function. So I do the iteration. And I have this kind of shortened. Pick A, get A over B, and then you have to get the graphical value and unnormalize that. So when you get the graphical value and unnormalize that, get this F factor. Reason to start with 1 inch is no clear reason. It just is a round number. So often I start with a round number and see how it looks. Other than that, I can't give you a reason to start with 1 inch. Anyway, when you calculated the K for that, I got 121, but I wanted to have 81. So that's much too high. So it seemed a lot too high. So I went back to a 1/2 inch, did the same analysis, got an F, and it was too low. And then sort of come into it by trial and get 80.9, so that's close enough. Critical crack size is 56. So that's part 1. Now part 2.
This F value, we have to use this function 1 minus A upon B power 3 by 2,
Yeah,
right?
right.
But we are getting some different, slightly different values than that one.
Yeah, you probably would be. It depends how you read the graph.
Right,
So not everybody, what,
We are getting F for A is equal to 1, F is 0.98.
no, it can't be.
Can we, from the graph?
yes, because here the graph shows between 0.9 to 1.2.
Yeah.
So let us take a value for suppose 0.5. If you take 0.5 as a crack, is the value is 1.
0.5. A by B 0.5. A by B 0.5.
The value of the graph is 1, right?
Yeah, the value on graph is 1.
Now you have to unnormalize it by taking,
1 minus 1 A upon B power 3 by 2.
yeah,
So then it comes down to
Okay.
0.5 doesn't matter.
when you do that,
Then you do it for point, A
What
by
are
B
you
equal to
getting?
0.2.
What are you getting for 0.5?
0.5 I'm not calculating. I'll calculate for first one. Or we'll calculate for 0.5.
Yes, it's better to calculate for 0.5
Alright, let us try.
because for 0.5,
yeah, I have a calculator too. We can all try.
A is equal to 2.
You saying the graphical value is 0.98.
it's coming right. For 1 inch, for 1 inch it is coming right for us.
Okay,
Okay, for 1 inch it is.
you want to try the other one?
We did that, but
Um,
it's right.
yeah.
Yeah.
That's a tricky thing. You have to get used to that, and I'm glad that you brought that up, because if you stumble over it one time, then you learn better, I think. So it is a problem to get that. The reason that they normalized like that is to make the graph go flatter. Otherwise, the graph goes really high and you can't read the early values. So, okay.
Right, yeah.
It-
1.37 is right.
Yeah, yeah. If you get a little bit different, like 1.36, that's okay. Because nobody reads graphs all the same.
Now it's coming 1.3696, so it is 1.37.
Okay,
Is right.
okay, yeah. We can't stand too many digits. If you have more than 3 or 4, it's, you want to try the other value, 0.5? Graphical value you said was 1.0, wasn't it?
Yeah, but that's okay, that's fine.
Then you got to divide that by, yeah. Now, the thing to keep in mind is that A over B gone to 0 is 1.122. Every other value has to be higher than that. If you get a value that's not higher than that, you made a mistake. Not so in bending, but in tension, that's so.
Should be lower, right?
In bending, yeah.
In all the cases?
No, in bending, you start with a big F at 1.122 for A over W of about 0. Then it goes down. Then it goes back up again. It's kind of tricky. So I don't have any problems with bending except later on. But I do it myself. If you can do this analysis and get the answer, that's good. It's good for you. Because this is one of the critical skills that you should learn. But more discussion on this, or? Okay, now, I want to bring up another point, so I bring that up with this. What happens if you, to the critical defect size, if K1C is doubled, but the yield strength is halved? Half mean that the yield strength now is 50 instead of 100. So what happens for that? Is here in part B. If the yield strength is halved, note that the net stress is already 50, you already yield at the plate. So when you already yield at the plate, fracture mechanics linear elastic is gone. So I say no defect. No defect allowed because you already yield at the plate, and we're working in linear elastic fracture mechanics here. So just to point out again, every time you play with this, you've got to watch out for how much yielding there is, and is it okay or not. So that's not okay. Now, question or more discussion on this one? I'll let this for a minute. Here's a little bit harder of a problem. So it's the second skill that you should learn. Cyclic life. I don't know if all of you remember how to do your integrations, but you should follow the integration like I did yesterday. If you've forgotten that, we can go back and look at it. But I want to do DADN, and I didn't write it here, so you don't have problem 6. I have to go find that for you. And pick A0 is 0.1, K1C is 100, the stress range is 10 to 40, and assume semi-infinite single edge tension. We want to pick semi-infinite so the F value doesn't change. Now the fatigue crack growth law. I guess is this. D80N is 1.144 times 10 to the minus 9 delta K to the 2.5. That was what we did when you had that set of data that you played with on Wednesday. Here's the whole solution. I didn't want you to see the whole solution right away, so cover your eyes for the bottom part, but you can look at the top. So D80N 1.144 delta K to the 2.5. I don't know if I can get a... Okay. There it is on the sheet, the D80N. Copy and paste works on this computer, which is a good feature. Saves you from a lot of writing. Let me... So you need, okay, initial crack size. You need the K1C to get the final crack size. Single edge in semi-infinite tension, F remains 1.122 for the whole deal. So you don't change the F. I'll give you a few minutes to work on that. If you have trouble with that one, it's okay, but you should learn it, so we'll go over that carefully, I hope. Yeah. Yeah, it's crack. So here's some of the things you would need. F equals 1.122 constant. Reason we make that F constant is if you do the integration and you change the F, it's a big mess. We started with crack growth rate law that we had developed earlier, and then initial defect size is 0.1, K1C is 100, stress is, range is 30, maximum stress is 40. So important in this problem is the stress range is the difference between the maximum and the minimum, and the final crack size, the thing fails when it hits the maximum load, so that would be 40. So those two things are different. So maximum stress of 40. Now, since F is a constant, you don't need to put the iteration like we did. You can just go straight off and calculate a critical defect size, which I got 1.58, and then put dAdn is the coefficient out front. This is the delta K, the delta stress, and then square root of pi a to the 2.5. Now, everything in there can be calculated except for the crack, which remains the unknown, or the variable. So crack size remains variable. Then you rearrange. The left side would integrate from 0 to final cycles. The right side from initial crack size 0.01, 0.1, final crack size 1.58, and you do this integration. This again is x to the n. So x to the minus 1.25 integrates, or a to the minus 1.25 integrates to a to the minus 0.25, and then you divide by the exponent, and then evaluate it at the two limits, and I got about 89,000. I don't know, did anybody get anything close to that? No? The two fundamental things in the application of fracture mechanics, how to find critical defect size and how to find cyclic life, are important. And I hope that if you look at this example, try to remember it, how to do it for at least 1 week. If you forget how to do it in 2 weeks, I won't be here anymore to be disappointed. But I'd like you to remember it for 1 week. Question? K1C, yeah. Yeah.
So I didn't know how to find out AF, so I got stuck there.
Oh, okay, yeah.
Otherwise, I had written down the relation for K is equal to delta K is equal to delta sigma root phi into F. That I had written down, but I didn't know how to find out the AF.
Yeah, always K1C. Yeah, that's a good point. Other discussions or questions? Okay, I have a little bit more on here, but I want to go do something for a few minutes here. That is, if you need to see that more, I can put it up later when we take the break. I could put it up again. But in this section, you've learned everything about linear elastic fracture mechanics that you need to know. Next week, we're going to start on the nonlinear aspects of fracture mechanics. But as a final thing in this, I have some case studies that I wanted to show you that are kind of interesting, and these don't take too much understanding. You just have to look at them. Some of these are actual failures, and some of them I made up. Some of them I didn't have the data for, so I estimated it. But all these examples follow the kind of fracture mechanics triangle logic. Remember the fracture mechanics triangle: stress on one corner, defect size on another corner, and material properties on the third corner. And usually you have to know 2 things and try to find a third. So here are 4 examples. This is actual failures, Comet aircraft. This is an actual failure that we had at Westinghouse a long time ago. This is a made-up example, and this is something that is actual analysis. So start with the Comet aircraft failures. Want to use fracture mechanics to look at the role of critical defect size. So this is a very simple application, critical defect size, based on some of the actual failures. I didn't know the properties. This is kind of an old aircraft, and I didn't know all the properties, so I made some up. However, one time I had a student in there from aircraft industry and showed him this, and he said, oh, those properties are pretty good. So probably pretty good. This is called the British Comet. It was the first commercial jet aircraft. They had propeller type aircraft before that, but it's the first commercial jet aircraft. So It's the de Havilland Comet, first one, 1949. Probably most of you weren't around in 1949, however I was. It had some noted failures related to fracture and fatigue. In the web page, you can find a list of some 20 failures. They had pilot error, sabotage, and some equipment failure. And the equipment failure is what relates to fracture mechanics. One example of equipment failure, I don't know how often it happened, but cracks coming from a window hole in the fuselage. When they made the windows here, I don't know if you can see them, they're kind of small, but they were pretty much rectangular. They had kind of sharp edges. If you've flown an aircraft now, you know the windows aren't real sharp edges. For good reason, you don't want it to fall apart in flight. These aircraft that failed, some of them, the fuselage burst in flight. And that's a very unsettling thing if you're flying in it. It probably don't live very long after that, but everybody on board is killed when that happens. So I wanted to look at the window crack issue. They used the 7000 series aluminum alloy, which has yield strength in engineering or English units about 65, and fracture toughness of aluminum is pretty low. I showed you some examples. You probably didn't memorize these numbers, but aluminum usually no higher than 35. However, 7000 series is particularly brittle and has K1C in that range. So not knowing what the design stress is, I said, well, let it only be 30% of the yield. That sounded like a good design stress, which is 19.5. And that one doesn't matter an awful lot in the analysis. So K1C, I picked the highest value. I did the central crack like Griffith's crack. And then if you do sigma squared to pi a for that, get A is 0.75 inch, or 2A is 1.5 inch. Now, that seems like a fairly big crack. However, when you have, use this solution, when you have a crack coming from a sharp corner like this, and it gets away from the corner would be a stress riser, but when it gets away from the corner, what the crack is seeing is the whole thing from tip through the window to the next tip. These windows were about 8 inches in the diagonal, so a small crack from the corner would appear as 8 inches plus. And so the critical defect size 2A was 1.5. When it got far enough away from the influence of that, then it burst. So that was a problem for this aircraft. That's just a quickie, but it shows you how fracture mechanics could predict that you would get a failure. Questions, comments? This is a second example, generator retaining ring failures, and this combines material and environmental interaction. So a chance to do what we did yesterday with the environmental influence. And most of what was done here is qualitative. Exact quantitative details wasn't always developed, but qualitatively tried to solve the problem. This is a generator. One of the big products in Westinghouse, of course, was power generation equipment, turbines, generators, nuclear power plants, marine engines, big marine engines, and stuff like that. So generator was one of the things. As you know, generators work like this. You have a lot of wires going through this, and then it spins the wires through a magnetic field, and as it spins it through a magnetic field, you get electricity generated, and you get, for each cycle, if you have a single pole, what they call, you get for each turn around, you get 1 cycle of electricity. We use 60 hertz in the US, so these mostly go 3,600 RPMs. Here you use 50 hertz, so it'd be a little less, but these were a little higher. Now, the wires that go back and forth would hang out on the end here, and as the thing spun, they wouldn't be in a good position. They would sort of flap around. So they put on a big ring to hold them in place, and that's called generator retaining ring. This ring then was made out of 4340 steel and fairly high strength. It is the highest stress part in the whole generator because it's just a ring. The rest of the generator has a big rotor, a solid rotor here. Okay, so this is what happened. A retaining ring failed in a peaking generator, causing a hydrogen explosion. The failure was a unit in California. Say a little bit about it. It had hydrogen cooling. They used hydrogen cooling, and when the thing burst, pieces flew right through the whole building and out into the parking lot, and then hydrogen gas came out and mixed with air, and hydrogen and air and sparks aren't good. The thing just blew up. So had a big hydrogen explosion. Now, it happened in the middle of the night, and the operators were at a remote facility monitoring it with computers and the like. So nobody was in the building. Nobody was hurt at all on this. But what happens was that there were other units that had similar rings, and there were concerns about these. I don't know how things operate here in India, but in the US, we have more lawyers than we need. So whenever there's an accident, people start suing everybody that they can think of. And everybody loses money except for the lawyers. They make money. So big lawsuits started happening, and the 3 responsible people that are the 3 concerned people were the manufacturer, which is Westinghouse, the material supplier that supplied these rings, and then the user. And they all had some fault. The user peaking generator means that it was used start-stop twice a day. This was originally built as what's called base load. So you'd start that and it would run for a month or so at a time without stopping. But when they started building new and bigger equipment, they went into peaking, which means they start it in the morning when people get out of bed in this high demand for making coffee or cooking or whatever, and then the demand goes down during the day, and then at night they come back from work and they start using power again, and then they start it again. So this had at least 2 cycles in a day, but it wasn't designed for 2 cycles a day. It was designed to be run continuously for a month or so at a time. What the concern is also with the suits, there were many other units that had similar rings. So there was concern about those units. If this one could blow up, what about the other units? Would they blow up? Now, if they blow up, it wouldn't look good, because you'd say, we already knew there could be a failure, and then you'll let another failure happen. Sometimes people get injured in failures. So that's not good. The other thing is, well, let's shut down all these units that have these rings. If you shut down all these units, then you don't have enough power for the peaking time. So it's a problem between, shall we let the thing run and worry about will there be another failure? Shall we shut down and then have not enough power? This happened in California. All the people in California like their electrical power, so they don't want to go without it. Retaining rings, as I said, were high strength, highly stressed parts, and the material was 4340 quenched and tempered steel. Here are some of the properties, and these were all in engineering units. What happened when we had that failure, they came to the research lab where I worked. I worked in a research lab, and our job was to take care of all the problems in the different divisions. So this was a generator division, so we worked on this problem pretty much day and night for a little while. Here's the properties of that material, and K1C pretty high, K1SCC was pretty low. So you remember K1SCC is threshold for subcritical crack growth in hydrogen gas for this material. Now, a couple things about this. This had minimum yield strength requirement of 150, but no maximum requirement. So the supplier, a steel company, thought the stronger the better. So they tried to make it as strong as possible because everybody was worried about plastic burst when this was made. This is probably made in the 1940s or 50s, before fracture mechanics was even invented and before people knew about hydrogen cracking and all that in bad environments. So in an attempt to get the best material, provide it a very high strength steel, and they exceeded that 150 by quite a bit. As you can see here, they went up to 180 yield strength. If you recall this from yesterday, if you'd stay at about 150 K1SCC, this is seawater, but the hydrogen is similar. I didn't have one for hydrogen, but at 150 K1SCC is fairly high, but at 180 you're way down here on the bottom. So by going over the minimum as much as they could, they went into the dangerous range here where you get real high, real low K1SCC.
Sir, how the different yield strengths are achieved with the same steel composition? Heat treatment. By changing the heat treatment, you get different yield strengths. Such a big range.
Yeah, you can have a big range in this field.
Yeah, did you answer her question? Oh, thank you. The hydrogen gas was used, they need a lightweight gas. The only other alternative would be helium gas. That's too expensive. Helium, as you know, is inert. Had they used helium, that would have been no problem because that's inert, but hydrogen was a bad one. So to do the best job possible, they tried to keep the gas very clean and pure. They had a dryer purifier to keep it pure. Now, I showed you this one, you might not remember, but if you have hydrogen, pure hydrogen, cracks grow in high strength steel. If you put a little bit of oxygen in, it stops the growth. Same thing here. Here is a kind of a dividing line. If you have hydrogen gas that's very pure, these solid points are points that would grow the crack. And the K1SCC line is here on the right side with a little bit of air. This is not just pure oxygen, but a little bit of air. You stop the growth. So doing this, if instead of trying to keep this gas very clean and pure, they had let it get a little bit dirty, they could have stopped things from growing. So some of the fixes to the problem, then pick a lower strength material in the area of 150 rather than in the area of 180. And they did that. They took all the units that had similar rings and replaced them one at a time in a very deliberate way, but they replaced them all with lower strength rings. Do not try to keep the gas pure. So instead of having this purifier dryer, they let it get some air moisture in and contaminate the gas a little bit. A little bit of contamination didn't hurt anything, Didn't hurt the weight of the gas, but stopped it. Now, in the design, fault of Westinghouse designers, the rings had some sharp corners, and the sharp corners were perfect regions for stress or crack initiators. This would be like the SN fatigue. The SN fatigue, when they ran this as a peaking unit with many more cycles than it was designed for, these sharp corners came into play and caused cracks to initiate. So cracks initiated in a high strength material with very pure hydrogen gas, just a bad situation led to the failures. And when they put these fixes in, then nothing more ever failed. So they had no more failures of this. So that's two examples. Now it's probably break time. So let's take a break for a break. How would you like, you think there's tea? Tea's there? Okay. How about, one of the things I have to do today is as soon as I get back to the hotel, we're getting in a car and going to Junta Alora area. So why don't we take, is 15 minutes okay? We'll do 15 minutes and then we'll have a 15-minute early dismissal and everybody can go home early for the weekend and do what you do on the weekend. So let's take that and come back about 20 after. So you did get the word. We will have holiday on Monday and resume on Tuesday. Now, I don't know if you know about this. As soon as we get back in the United States, we will face a holiday of our own. I don't know if you've ever heard of this, Thanksgiving Day, when everybody has to sit around and eat big turkeys. I hadn't seen turkeys on any menu here. Do you eat turkeys in India? Turkeys are very big birds. We have them in the wild and in...
Generally not.
What?
Generally not.
Generally not.
Only the five-star hotels might serve you the turkey.
They don't grow them here?
No.
We have big farms. They're the domestic turkeys. And then there's turkeys in the wild. People who like to shoot animals like to go out and shoot turkeys. And the way to shoot a turkey is to put this thing in your mouth and you go gobble, gobble, gobble with the thing in your mouth that makes you sound like a turkey. And then the turkey thinks either it's a friend or an enemy, and either way they try to come check it out, and that's a big mistake for that turkey. If the person can shoot his gun okay, which most people who shoot turkeys can shoot pretty good. But people who don't like to shoot animals and kill animals, let somebody else kill them for them and then buy them in the grocery store. And get this big turkey, and then we make a bread mixture with onions and spices and stick it inside the turkey. Where it used to have his insides is a big cavity. You stick this mixture inside and cook the turkey half of a day or so, and then it cooks the turkey meat and the inside stuff we call stuffing because it's stuffed in the turkey. And then people sit around eating that, and turkey meat has some chemical in it that makes people sleepy. So after they eat big turkeys, they fall asleep, except for the women who have to clean up and do the dishes. Usually the men are falling asleep and the women are cleaning up and doing the dishes. So, and then that's our holiday. Anyway, here is a problem that's not a real problem, but a simulated problem, offshore oil rig. The offshore industry was pretty popular, and I got involved with some people doing some calculations about pipes. They need a pipe going from the bottom of the ocean, or in this case, Gulf of Mexico, maybe 1,000 meters or so, up to a rig sitting on top of the ocean, and it has a lot of cycles, a big fatigue problem, because you get the waves. And you don't know how big the waves are. They have numbers between 1 and 10, 1 being a very calm sea and 10 being a really rough sea, so bad that that's not good. Anyway, I gave this problem to my students. I used to teach fracture mechanics to graduate students. These are students who already have a bachelor degree in engineering and then were studying some aspect of something. It has so many different aspects that maybe you can't follow. If you can't follow everything, okay, I just want to show you some of the things you can do with fracture mechanics. I'd give them that problem as part of their final exam, and depending on how many things they looked at, they'd get a good grade or a bad grade, not necessarily getting a right answer, but this. So here's the input. I assumed a structural member, which is 25 by 100 millimeters. Anyway, in the university, we use SI units, so I did this all in SI, so you'll be more comfortable maybe. But 25 by 100 cross-section, it is under constant tensile stress of 200 MPAs, but the ocean waves give a bending of plus and minus 50 on top of that 200 at about 7 cycles per minute. I picked 7 cycles per minute because I was sitting on the beach one day counting how many waves came in a minute, and I got about 7 some of the time. I assumed that the non-destructive evaluation could find a flaw of up to over 1 millimeter. So it could have a flaw somewhere of 1 millimeter or less, and then we use that as a starting flaw. The question is, pick the best material to survive 10 years inspection at normal stress, this particular stress situation. Then pick the best material to survive a hurricane that does not change the tensile stress, still 200, but then the wave stress, the bending, is plus or minus 250, still at the same frequency. It is difficult for this. Oh well, here's the material properties. 3 materials to look at. Material A was a fairly low strength material, 300 MPa yield. Material C was higher strength, ultimate tensile strength. So as the strength goes up, K1C goes down. So it went from a really high K1C to a fairly low K1C. Crack growth rate is the same all the way across. I assume there's no change. The K1 SCC, I picked 3 values. For the higher strength, it's fairly low. For the low strength, fairly high. And then there's a threshold fatigue number, which is this. And then the growth in seawater, I picked this as growth in seawater. So all those are inputs. All those can be used in some way or other to look at this. Now the model I used was edge crack. The tension load was like a single edge tension specimen. I don't have that here somewhere. Single edge tension. The bending load was like a single edge bend. Here is the crack size. So 70 by 100. This is 1 millimeter to start, but it could grow. So for the 10-year inspection period, I looked at crack lengths versus K and net section stress. I worried that this thing could fail due to net section overload or to K1C, either way. And for the initial length, then I picked 1 millimeter growth in cycles or in time if you get above the K1 SCC. Could this last 10 years? I looked at the cycles and the times. 7 cycles per minute, 1 day is already more than 10,000 cycles. 10 years is already 36 million cycles. So that's a very, very many. And these are the numbers of hours that go with that. So 1 year is a little bit under 1,000 hours, 10,000 hours. Okay, K solutions. SCT is the tension, SEB is the bend. Tension has 200 MPAs, bend has 50, plus or minus, well, range of 50, it's plus or minus 25, so the range is 50. Here's the K solution. And in linear elastic fracture mechanics, you can add Ks if it's all mode 1. Remember, yesterday we talked about mode 1 and mode 2. You can't add the Ks, but if it's all mode 1, you can add the Ks. So had these, this is the single edge tension for the constant stress. This is the single edge bend. This is where, as we were talking earlier, this goes way down, but you have to unnormalize it. So when you unnormalize it, this factor is fairly small to begin with, so the F goes down, and then this factor gets bigger, F goes back up. So it's a little bit of a mess to do. So initial crack 1 millimeter, A over W, so forth, and then I got the F, which is 1.122. It's such a small crack, it's the same in both. 1.122. So K due to tension at 1 millimeter and 200 MPAs was 12.58. The range then for the bend at 50 was 3.14. So adding them together, you get 15.72. Now that's for 1 millimeter. So in order to kind of do the analysis, I looked at different crack sizes and made a big chart. Rather than trying to solve backwards, I made this big chart. So here's an example. A is 20 millimeters, and here are the K values. Total K is 81.9. The other thing to worry about is net section stress. So for tension, net section stress is just load divided by area. And when you do net section, then you have to take away the defect. This is not to get the K, but just net section. So for a crack of 20 millimeters, you have to take the load. This is the load on top, and this would be then the net area, and that's the thickness. So 200 MPAs is net section stress due to the 200 load. For the bending, the net section stress turned out to be 78. Add them together is 328. So I made this chart. This is what I had to start. 1 millimeter. It was such a small crack that then didn't change from 250. But as you go up bigger and bigger, here's the 20 that I showed you. For all these different crack sizes, I got different Ks applied, net section stress applied. So I did that so I could go into that chart and look around to see what would be critical defect size. So let's start with material A. K1C is 200. If K1C is 200, it exceeds 40 here. It's down here somewhere where I didn't calculate it anymore. The yield stress was 350. So for the yield stress of 350, the defect size would be 25. So this thing would fail due to net section stress, but not due to K1C. So I picked that as the failure point for material A. Doing the same thing, material B, going with its K1C, critical crack size is 30. So K1C was 120, and this fails before net section stress. So this fails due to K1C, this fails due to K1C. Those are critical crack sizes for failure. Now, material A with EAC, I picked the crack size to get stress corrosion cracking started. Those are the three values that I got, and I went back to that chart. For example, K1 EAC of 50, pick out 50 here. It's a little less than this 10, so I made it be 9. This is somewhat rough, but it's just putting things together like that. Now, looked at time to fail due to stress corrosion cracking. Here, the crack starts to grow due to stress corrosion cracking at 19, but it fails at 30, so it could grow 11. So for example, if the crack grows 11 millimeters due to DADT, it would fail. So I got for that, it would fail due to that in about a little more than a year, 11,000 hours. That's not enough life. And material C, it would grow only 10 millimeters, and due to its growth rate being faster, it would give only a little more than a month. So concluded that once you get to stress corrosion action, you don't have enough life to really last. Material A would have the longest life, but want to do fatigue crack growth, and I had trouble with picking the F. So I picked F as 1.122 and did some of the analysis that you had done earlier today. And here is the crack growth rate, and here's the cycles to fail. Since the fatigue didn't change, this is material A from 0.001 1 millimeter to 30 millimeters, where it fails by plasticity. I got a little more than 1 million cycles of life. One year though of cycles is about 3 million. So 1 million cycles of life is not very good. Life of 1 million cycles is about 0.4 of a year. So that's too short. Since didn't work for picking F at the initial site, I didn't upgrade it because this is a conservative value. So in all the materials, the crack is growing too fast for 10-year life. The only chance is no crack growth. No crack growth then comes from fatigue threshold. So I went back to look at fatigue threshold. What happens if you have the initial crack of 1 millimeter and stress of 250? For this case, for example, here, K, then delta K turns out to be a little more than 6. So for no crack, you have to stay below the threshold. The delta K of a little more than 6 only works for material A. I don't know if we want to go back and look at the this thing properties. Way back here. The only saving thing then was delta K threshold. Here is 765. The only one that was above 6.3 was this material A. So after doing all that messy analysis, get back to the very beginning and say only chance is delta K threshold. If this is 6, then material A has delta K threshold of 7. I'd pick material A and hope that the crack never grows. That's the only hope for this material. Any questions or discussion? It's a lot of factors and it's a little bit complicated. Just want to show you that fracture mechanics can be a little bit complicated when you throw all this stuff together, and then have a little better success for part 2. If you have a hurricane, then the delta stress is 250, so it ranges from minus 50 to plus 450. 200 plus this, 200 minus this. Now, we have a little bit of trouble in fatigue. What do you do when the stress is minus? We talked about closure and all that kind of stuff. Very often people just throw that minus away and say, well, assume it starts at 0, because the crack's probably going to be closed for minus stress, and you wouldn't really get any fatigue due to the minus stress. So here's a table again of K's and net section stress. Now, at the peak, K is 28 and stress is 450 for just a 1 millimeter crack. So material A in a hurricane would be way above the yield. It was the yield was only 300, so you'd be way above the yield and throw that material out right away. So material A yields, throw that out. Material B has a critical crack size of 17 millimeters for this stress. Somewhere down here, 120, I interpolate it. It was K1C is 120, so somewhere 17 millimeters. And material C, K1C was about 80, I think, so it has a little bit more than 8 millimeters. So just pick 8. Look at material B. It could grow a crack from initial size of 1 millimeter to 17. Now, in doing this analysis, I didn't say that the crack might have been growing during the regular times. I just say let's start with the initial crack 1 millimeter and see how life plays out with the 1 millimeter crack due to this big overload in the hurricane. And then crack growth rate due to that high stress cycle turns out to be then life doing the integration about 1.55 times 10 to the 4 cycles. The cracks will all grow. They're above threshold. The cycles per day we had was 10,000, if you recall cycles today. This is about 15,000. So 15,000 cycles is about 34 hours. The material C would only grow from 1 to 8, and that would last about 17 hours. It's about half of that. So my guess here is pick material B for the hurricane. Just to show you how you can throw many things into fracture mechanics analysis, and if you were a student in my class, you would have to do some of that analysis, and the more you did, the better. Sometimes you take the number of pages they have and count how many pages they have. People with more pages get a better grade than people with fewer pages. Especially on a problem like this, the answer, somebody else might pick a different way to do the problem and get a different answer, but they shouldn't get too much difference. So comments at the end, this is a detailed analysis, made many simplifying assumptions. So here's a strategy when you're doing kind of analysis for fracture. The best thing to do is to start very simple, but be conservative, because you don't want to do a lot of work if you don't have to. I always tell students engineers should be lazy. They try to make the world easier, not harder. So you should make the problem easier for yourself, not harder. So if you do a simple conservative analysis and everything turns out okay in the end, good. But if it doesn't turn out okay in the end, then go be less conservative, do more analysis, and then in the end you can see if you actually make an analysis that works. Now, this is supposed to say software. I don't know how software got in there, but somebody put software. A lot of software, and I'm going to talk about that next week. I never encourage people to use software if they don't understand what you're doing. If you probably have, some of you have experience using a program, you don't know what it does, You pick something a little bit wrong, and you get a really bad answer. And if you get a really bad answer and you don't know what you're doing, you don't know you have a really bad answer. But you might anyway have a really bad answer. So I like people to go through a problem like I did, paper and pencil. And if you then understand the whole process and know what you're doing with paper and pencil, good. Next time you go back, use some program. And you have an idea what you should get out of the program, and you can get a better number, but at least you know when you get the number out of the program, it looks okay or it doesn't look okay. If you have no idea what you're doing and you use a program like that and you get an answer, you don't know how good it is. So that's one of my philosophies. Here's another program or another example, and this is an actual problem called pressurized thermal shock. And told you on Monday when I showed you where we lived in Tennessee, we have a national lab near us that is Oak Ridge, called Oak Ridge National Lab. They've done a lot of work in energy-related things. And one of the things they had worked on for a long time, this is maybe 20, 30 years old, but they worked on that, is a nuclear reactor accident where they get cooling water sprayed on a pressure vessel to prevent core meltdown. We have an agency in the U.S. that's a government agency regulating nuclear power plants. Fossil power plants, nobody cares if they fail. But if a nuclear power plant fails, it's a big disaster. Could be the end of the industry. So they regulate it very strongly. And one of the things they do is to make up problems. They say, what would happen if such and such a problem happened? Something broke here and you have a problem. Would you be safe or not? So engineers from utilities, like the power generating companies, from the manufacturers like Westinghouse, all get together and work on that problem for maybe a couple years. And they come back and say, oh, we solved it. Everything's going to be okay. So then the Nuclear Regulatory Commission comes up, but what if this thing breaks and at the same time an airplane flies and lands on top of it while the thing is breaking? Next problem. So they go away for 2 years and they work on this problem and they come back and say, oh yeah, we solved the problem. Everything's okay if this breaks and an airplane falls on it while it's breaking. Okay, now what if thing breaks, an airplane falls on it, and there's a terrorist over there setting off a bomb all at the same time? So they go away and they work on this problem for another 2 years and come back and say, oh yeah, everything's okay if the thing breaks and an airplane falls on it and a terrorist comes and blows up something. Yeah, it will be safe. It's kind of a child's game, like a computer game where you do funny things, but it keeps a lot of people working for many years. So people get paid to do this. They actually get paid to do this, and the Nuclear Regulatory Commission feels like they're doing their job. They're regulating things. So this is one of these what-if problems. This is at the very beginning. So the nuclear reactor, I don't know if you have some here in India? Nuclear power plants? Yeah, they're very simple. You use a reactor core that cooks some water like you would on the stove. When it cooks the water, this hot water goes out and either goes through a heat exchanger, which is what we built at Westinghouse, and then the hot water drives the turbine. Or it doesn't go through a heat exchanger. That's the other model. The one with a heat exchanger is called pressurized water reactor, and the one without that is boiling water reactor. But in every case, this goes out and drives the turbine. So if you lose the water, the cooling water, it's not good because the reactor keeps going and going, and then they worry it melts, maybe goes into the ground, hits groundwater or something else that's not good. So in order to save that, if there is an accident where they would lose all the water, the cooling water, And it would be very rare because they usually have, I don't know, 3 or 4 loops coming into the reactor, and to have them all fail at the same time is not very probable, but they like to do these examples that I told you about. And so this is one of them. They lose all the cooling water at once, and then they shoot cold water onto the pressure vessel. And this explains it a little bit. When they lose the cooling water, they have a rapid cool down by spraying water onto the vessel, and then they get pressurized shock or thermal shock, and then also pressure builds up inside for some reason. I don't understand how the pressure builds up, but I understand the thermal shock. As you know, if you have a big wall, these walls are 10 inches or more, maybe 200-300 millimeters thick. And if you put cold on one side and hot on the other side, the cold wants to contract, the hot wants to expand, and that creates what's called thermal stress. So here's a vessel, and here is the core region where the reaction takes place, and here's a critical area where you would get meltdown. Now this looks pretty small, but it can be 200 to 300 millimeters, so it can be fairly thick. When they get the initial loss of coolant and hit it with the water, the temperature comes down like that. So this is blowing around, but this is time in seconds. So 2,000, 3,000 seconds is several minutes, a good part of an hour, but not a whole hour. And what happens here then, the pressure is dropping, but then comes back again due to some method that I don't understand. So with time, with this change in temperature, change in pressure, you get stress profiles. The cold side would be high stress, the hot side low stress, and with time going from 200 to 2,000 seconds, you get these profiles. Now this is thickness in inches, and this was about 8 inches. So that was just one example they picked, 8 inches. Now they also said there may be a crack, and they used what they call reference crack. The reference crack was about quarter of the thickness. So in this case, 8 inches thick, it would be about 2 inches in, and then 6 times that, so 12 inches by 2 inches. That's quite a big crack, but that's their reference flaw. And remember, this is all hypothetical game playing. It's not real stuff. So because there is that stress profile, and because there is a crack, they get stress intensity factor, K. K with time has this feature. As you get longer and longer crack, you get higher K, but since the stress goes from high then to low, as it gets into the low stress area, comes back down again. So the K goes up, peaks, and comes back down again. So that's what the K profile looks like. Now, because the temperature changes, and this is a material that has ductile to brittle transition, K1C follows this. It's hard to see it, but follows this. And then they use crack arrest. We talked about the crack arrest test real briefly. That is, if a crack starts to run but then hits a tougher area, it should stop. So there's K1C for initiation, K1 arrest for stopping. And the K1 arrest line is behind the K1C line. But because the material's changing temperature, this transition changes with temperature. And so from the high temperature in the beginning to the lower temperatures at the end, the K1C changes like that. So here's the temperature profiles. With time, you can see it changes and gets lower and lower temperature profile. Here's what could happen then. If the crack then has a K, here's a K that gets above K1C, the crack should run. So here we're getting above K1C, the crack's going to run. But then because the K distribution is funny due to the varying stress pattern, it would come back and hit K1C again, but it doesn't stop at K1C, it stops at K1 arrest. So this is the K1 arrest line. So what would happen here, crack would jump all the way to here and then stop. Now, after it does that, the properties keep moving through the thickness. So the properties are going to change again. And eventually then this point is going to lie to the left of the K1C line, meaning it jumps again. And then it can hit an arrest line, which means it stops. All again, this, as I told you, is hypothetical. So the procedure is run arrest. Run, stop, run, stop. And the game then is to see that this run arrest doesn't go all the way through the wall. Leaking, you know there's a failure about to happen, but leaking is not good when you have irradiated components and irradiation to leak out. So they want to have run arrest, finally in the end, complete arrest, and not through the wall. And so when they did this analysis, they found that it, in fact, the analysis said it would arrest and not get through the wall, so it was safe. So this is worked out as being safe. Now, one of the problems is that there are experimentalists and there are analysts, and the analysts did this and said everything's okay. The experimentalists said, oh, we don't believe it. You know, prove it to us. So they actually did a big set of tests on what they call test vessels, but the test vessels were pretty big things. They're about 6 inches wall thickness, and they built a huge pit and they put it in to shock it. Sometimes they use very cold things like liquid nitrogen or some kind of slurry that would make it cold. Anyway, they put it in a cold bath, and they got cracks to actually do this, run and arrest, run and arrest. And the experiments showed then that this thing did not fail by going all the way through the wall, but had its final arrest before it went all the way through the wall. So that was good. Questions on those? Those are some examples. I thought sometimes it's interesting to see that people actually use fracture mechanics stuff. Now, here's an example that I wanted to go through with you. I would let you work this out, but it's a little bit complicated. Oops. Let's see. I think I have to. Okay, I found it. Some of these things are hidden away in secret places that only I can find, and sometimes they're hidden so well that I can't find them myself. So, unfortunately, found this. One of the things I told you that we do in fracture mechanics is failure analysis, and people do this more than they would like. But if you do failure analysis, you make a pretty good living out of doing this because things fail a lot. And when things fail a lot, I told you, people sue everybody, at least in the U.S., because we have more lawyers than engineers, something like that. And anyway, this is fractography. And when I do short courses in the U.S., I often have a short course in fracture mechanics and fatigue followed by a short course in fractography. That's not mine. I'm not an expert in fractography. The only time I'm an expert is if nobody else in the room is an expert. Then I can be the expert. But as soon as another expert comes in, I lose my expertise, just like that. Anyway, we do this fractography, and I like to show them how you can use the fracture mechanics and get a quantitative answer. So we're going to use fracture mechanics as a guide to do this, and my problem is going to have an edge crack body that has this look at it. You can look at the fracture surface. You imagine then a wall that had broken in two, and you're looking down on top. And one of the things you might see is a black area. You might see shiny area that is looking like fatigue. Fatigue often comes out shinier than fast fracture. You might see a fast fracture area. In fatigue, in some materials, you can look under a microscope and see what's called striations. I don't know if any of you ever encountered that. They're little ridges, and each ridge is one fatigue cycle. And they're fairly small. So if the fatigue crack growth rate is 1 × 10⁻⁶, you would see that size of ridges, that distance between ridges. Anyway, to do an analysis, you can look at several things, which is final failure, crack growth rate, initial failure. And I had this problem that I made up pretty much, but wanted to do failure analysis kind of thing using quantitative fracture mechanics to do it. So a lifting device, I said, had a 1 by 5 inch cross section and was supposed to carry 75 kips. This is, of course, in engineering units. And it operates about 5 times an hour and had a design life of 25 years, but unfortunately it failed after 7 years. An examination of the fracture surface found this. And I'll show you the picture again. Small area on the edge was discolored, and that size given. And then there seemed to be an initiation, that seemed to be an initiation point for fatigue. And then the area around that looked like fatigue until the crack grew 1 3/4 inches and then had a final failure. So it was 1 by 5, and I used the edge crack model again that we used a lot to do this. Here's the picture. That small area that's dark looked like an initiation area. This looks like fatigue. This looks like final fracture, and those are the dimensions. Now, I took the generic properties for steel from that graph I showed you on Wednesday. Had delta K threshold was about 6. K1C is about 120. So I want to do an evaluation of this using some of the principles that we learned to see if we can figure out what caused failure. And this is made up, so I kind of stacked everything in my favor to come up with one conclusion. Now, I'd like to start here with final failure and see how final failure looks like. And in order to do that, okay. told you about hiding my stuff. I have to go back and get here it is. We'll have to go back and forth between these two. Anyway, this is the analysis I did. The thing, if you recall, said that final failure would happen at a K1C maybe of 120. Then I want to look at initiation. This is my process of thinking. If these two give me some idea what happened, I want to look at fatigue life. So start with final failure. And I use the single edge tension model that we played with earlier with a crack size of 1.75 inches. A over B is 0.35. I got the capital F about 187. So the stress on this 0 to 75 divided by 5 by 1 is about 15. So that would be the stress. So then it should fail with a stress of 15 when it reaches K1C at 1 3/4 inches. When I did the K analysis here, it didn't fail. It didn't get to K1C nearly at all. It got to about 66. And I said K1C should be about 120. Now, most K1Cs have some range, plus or minus 10, 15%, but this is more than plus or minus 15%. This is awfully low to have a K1C failure like that. So I went backwards and said if K is 120, then getting the critical stress was not 15, but actually 27. And the maximum load to cause that would be 137 and not 75. So I was saying then it looks like it had a very high load at some point. Then going back to the second part of the analysis, the initiation. Initiation flaw, I used part through flaw, but you could use whatever. Part through flaw K is like this, 1.122 sigma squared of pi a divided by q. And if the stress is 15, the delta K is 3.7. That's not good because the delta K threshold was 5, I think. I have it on the next one. This one's doing tricky things. Okay, maybe it'll settle. Anyway, if the stress is really 15, then the delta K would be 3.7. Now the threshold was 6. So if the stress was really about 27, as I got from the K1C failure, that would have gotten enough for the crack to grow. So in order to make that crack start growing, it looked like there was a high load. Now I also did fatigue analysis, and in 7 years, I picked 5 lifts an hour, but only had them working 12 hours a day. I don't know if and working every day, so they probably had some holidays like you do on Monday and weekends and stuff, so this might be a little overestimate. But then I did the ADN delta K analysis and found that we should have had a life of at least 400,000 cycles, and K1C analysis, no, the life analysis is here. I did a life analysis in a sort of a crude way and got a little bit more than 400,000 cycles. So 400,000 cycles, by my analysis of life, should be much greater than the 7-year life, but it wasn't. So the reason it would have a shorter life then is because it was overloaded and had higher stresses than what we assumed. So my conclusion here was from these 3 points, K1C, delta K threshold, and fatigue life, that this seemed to be consistently overloaded. So the reason for failure was overloading here by the people who use this equipment. Any discussion, questions on this? I made this problem up, as I said, when, as I told you before, when failure happens, everybody sues everybody. And when we worked for Westinghouse, our job was to prove that it wasn't the manufacturer at fault. It was somebody else's fault. So I made this problem up being the user's fault. If it's the user's fault, it's not the manufacturer's fault. So in the case, this fits my philosophy that the manufacturer is never wrong, it's somebody else's fault.
Is there any possibility to measure this fatigue cycle from the appearance of the striation number of
Yes, yeah. Yeah,
very so microscopic level.
is what?
A microscopic level, the counting that.
Yeah, I had that in there, but some people didn't like striations, so I took it out. I had that in the analysis. Is a good point. Normally, you have the SEM or the TEM. TEM does a better job of finding striations than the SEM because I think it has a higher resolution. I don't know, does anybody use microscopes here? You do. You use SEM? You ever use a TEM? TEM has better resolution than SEM?
But TEM will need the thin film.
Sample
Yeah.
size is very small here, so may not be possible for all the cases.
Yes. Yeah, striations are really small.
In the second part, appears in striation is a ridges, which marks. So that is the stopping of the cycle.
Yes.
So again, to differentiate that one.
Yeah, you could put a lot more things in here if you were cleverer than I am. If people, say, overloaded it once in a while and then ran it regularly, you would see those beach marks because they'd overload it and they get funny. You get bigger striations and then they go back to the regular thing and maybe the crack doesn't grow at all. But yeah. Do you see marks on your composite materials? You don't see anything.
That we don't see for the fatigue.
You don't see fatigue. But you do fatigue testing,
No, not.
just fracture.
On composite, no, we are not yet started.
Okay. Yeah, the idea of finding striations is very old. People were doing it back in the 1960s
I
even.
think that is only for metals. I don't think it is possible on composites.
Yeah, I think you're right.
Basically, it is because of your shear stress going on in 45, so you get that striations in you have a dislocation slips.
Yeah,
That dislocation slips creates your striations.
yeah.
It's not a mechanism in composites.
The one material that shows good striations is aluminum alloys.
That should show.
They show good. Steel sometimes not. I don't know any other metals. You have any experience with other metals? So he should do that as a third thing and look for big striations. If he'd find them, he also know that overloading took place. Okay, that's all I wanted to cover for today. If you remember the rules, no class on Saturday, Sunday, and Monday. We're going to come together Tuesday, and I'm going to give a little bit, I guess we're going to try to pick up an extra lecture, see how it goes on Tuesday and Wednesday. But I hope you have a good weekend. I'll give you the report from Alora and Ajanta and Alora when I come back on Tuesday. So I hope. One of the problems we're facing is cash money. I think we're probably not the only one. I think there may be how many people, a billion people facing that same problem? The only way to not have that problem is not have any money. So if you don't have any money, things are fine, but people don't like that.